I am sharing my screen, my entire screen. Okay. All right. Welcome to a Sunday class. I'm sorry to have taken 2 hours of your Sunday because there was a mic malfunction the other day, and I still can't fix it. I'm basically talking into my laptop's mic. I'm not using my headphone mic, so I'm not sure why that happened or what changed. Um, anyway, so let's jump right in. Where were we last time, by the way? Okay, that's wormholes. Maybe not. All right. So we were dealing with forced simple harmonic oscillators. Okay, forced simple harmonic oscillators. All right. We looked at resonances. Right. There are two types of resonances: velocity resonance, where the velocity goes maximal. Okay, and that happens at S over m. Right, and there is displacement resonance. This happens at minus, can somebody help me here? Or something like that, I guess. Maybe I'm wrong. Hold on, let me check. 2m squared, yeah.
No, sir, it's right.
Okay, so these are the two kinds of resonances, and velocity resonance is where the energy transfer is maximal. Okay, you transfer as much energy as possible to uh, to the oscillator. You're trying to force the oscillator to vibrate, and if you do it at the frequency of the velocity resonance, if you're applying frequency, I mean force, the frequency of the force that you're applying, if that frequency matches with this frequency here, omega equals square root of s over m, then you're transferring maximal power to the oscillator. Okay, and I gave you an example of wireless energy transfer, wireless charging. Okay, and wireless charging is an emerging technology. It is not still perfected yet, but when you use this velocity resonance, when you use this velocity resonance condition, you can transfer high amounts of energy without much dissipation to your batteries. Okay, so I gave you an example of that wireless charging the other day. It's an emerging technology, as I said, as I told you guys. So it's useful to remember. Okay, and displacement resonance, it happens at a slightly lower frequency than the velocity resonance. This happens when the displacement is maximal, and there are many places where you don't want displacement to be maximal, like earthquakes. So what do? Okay, you can modify the looseness of the soil, the mass, the resistance offered for the offered by the building, and all that. Okay, you can modify that to minimize the displacement. Okay, and we were talking about Q factors earlier, so I'm going to connect it to resonance. Today's part of the topic is going to be connection of Q, which is the quality factor, to the resonance curves. Okay, we have earlier looked at quality factor, Q factor, as number of cycles the SHM goes through, number of cycles the SHM oscillates through before the energy decreases by what?
So
By
1 by
factor of E.
1 by E.
1 by E.
1 by E. Okay,
One by
by about a V, about a factor of E. Okay. Is there any other explanation, any other definition for Q factor that we came up with?
The total energy by energy lost per cycle.
Good. Okay. Total energy stored in the system divided by energy lost per cycle. Okay. I am trying to remind you guys these because you will be using these Q factors in your engineering classes, and this course's name is engineering physics. Okay. So you need to know these stuff. Okay. Now we will go for another definition of Q factor. Okay. Now let me talk about resonance curves. No, okay. Before we talk about that, I'm going to introduce something else. I'm going to introduce power absorbed or supplied to the SHM. Okay. So what is the power supplied to the SHM? You are supplying, you're oscillating, trying to oscillate the SHM using a force F naught cos omega t, let's say. Okay. So this is the equation for the force that you're supplying to the SHM, to the oscillator. So you have an oscillator, it's moving up and down. Okay, and you're trying to oscillate it from outside. Okay, like using an electromagnetic wave, let's say. Okay, if this is an electron, you're supplying an electromagnetic wave, and the equation for the electromagnetic wave is this. It's F naught, which is EE times cos omega t. All right. So if this is the force, what would be the power supplied by this force to the SHM? Anybody?
So force time velocity
Good.
of the
Good.
so average power is instantaneous power.
Okay. For now, which is instantaneous power, we will go for average power, average over a cycle. Okay. We will immediately go for average over cycle, but for now it is instantaneous. Okay. So it's force times velocity. You're right. So it's F naught cos omega t. And what is the equation for velocity we wrote down last time? F naught over Zm cos omega t minus phi. Right? This phi comes from the Zm. Remember, the Zm is a complex quantity. We wrote down as a complex quantity. We wrote down as Zm e power I phi, and then we took the phi to the numerator. Remember that? Yeah? Maybe not. Okay. So you have the force, you have the velocity. Okay, that is your instantaneous power. Now, what is the average power? The average power is dt from 0 to t, 1 over t, right? Yes or no?
Yes, sir.
Okay, so you get an idea of how much power is dissipated per cycle. Okay, so P average is integral of 1 over t F naught F naught square Zm cos omega t minus phi dt from 0 to t. All right. Okay. If you do the integration, I'm not going to do the integration. If you do this whole integration, you will end up with F naught square over Zm. Zm cos phi. Okay, this is your average power supplied to the um, to the to the SHM every cycle. Okay.
Yes.
So obviously, if you want to have an intuitive feeling for this, if you increase the resistance of the SHM, will the SHM absorb any power? I mean, will the power absorption increase or decrease if you increase the R in your SHM? There is the resistance R, right? Will it
Sir,
increase?
first increase and then decrease, sir.
Why is that? Why would you say it increases first? Let's talk about average power then. If you increase R, I mean the resistance of the power, resistance of the simple harmonic oscillator.
Sir, this is the power dissipated by the simple harmonic oscillator.
For now, we are talking about the supply power. Okay, let's talk about the power dissipated then. Okay, let's talk about that first. Okay.
Sir,
So
if
this is
the R's resistance is increasing, then the power will continuously increase. If the power dissipated would continuously increase.
increase. Okay. 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 Fair enough. Fair enough.
So power supplied is not something that is internally related. Like we are giving the power from outside of the source now. So whatever will be the resistance of the power system, the power will be not affected.
Okay. 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 Thanks for pointing out a problem there. There is a misunderstanding here. See, let's say, okay, let me give you an example. Let's say you have a tank of water, okay, and you are supplying water from outside. You're forcing. There is a pump, a motor that pumps water to this to the tank. Let's say the tank is full, okay, and you're pumping water like this. Can you, depending upon how much water there is, the the effectiveness of the pump changes or not changes? Would it change or no?
So in this system, it will affect because the pressure will be.
Power will keep changing because there
Sir, the
will be
effectiveness
certain
will be changed.
increasing
Exactly.
from where the water is.
Exactly. So if the tank is full, then you have to supply more power. You have to supply more power to the engine to supply more water into that, to pump more water into that, right? So depending upon the system, if your system is not able to, if your whatever system you have, this is your system, whatever system you have, depending upon the state of the system, the power supplied changes. Okay. If the system accepts what you're trying to give it, then the power supplied is large. If the system doesn't want to accept whatever is given from outside, then power supplied goes down. Does it make sense?
Yes,
Sir,
sir.
sir, there is a doubt.
Yeah.
Sir, if the system doesn't want to accept, then the power supply should be large now. Because if we take this example, if the system if the water level is below that level of pipe, okay, but as it goes above, the system has to supply extra power to raise the potential energy of the water also. Same
Yeah.
goes for the spring. The stiffness of the spring will affect its potential energy. So, if the system is resisting the acceptance of power, then the power supplied should be more, no?
Okay. 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 What I'm talking about is average power. That's a good point. Very good point. What I'm talking about is the average power. Okay. Number one. Okay. Let me try to answer that. let's look at the equation first. Let's look at the equation and see what the equation says. Okay. Now the Zm here, where is it? It's in the denominator. Okay. Zm has, what does Zm have? Zm has square root of r square plus xm square. Am I right? Am I right?
Yes.
So if the resistance is large, okay, what is going to happen?
The Zm will increase, so power average will decrease.
Yeah. So
So
what
Zm
is
will, so Zm will be large, and then the power average is inversely proportional to Zm, so that will decrease.
yes, but there is a cos phi also. Cos phi, what is cos phi? Is r over xm, r over Zm. Right?
Yes.
Okay. So for cos phi, you do this substitution. There is a Zm square and there is a r. Okay. Now, even in this case, there is a numerator r, but there is a denominator r squared. Okay. So if you increase the resistance, the average power supplied actually decreases. The system doesn't want to take the power in. Okay. In this case, in the water case, if the amount of water that goes in is lessened because of the pressure from the top, the increase in the potential energy is minimal. Am I right? Do you understand what I'm
So
saying?
that was the point that I was trying to tell, that if the system is accepting the power and that we are providing, so the same effect we will achieve the same effect easily, and the system is not accepting the power, then the same effect we will have to add a lot of power to achieve the same effect.
Yes, exactly. At a constant power, the power when externally, when you're trying to supply some power, with some force, F naught externally, the power accepted. Okay, here the power accepted depends on how much the system is willing to accept. Okay, if the system is not willing to accept power for this constant F naught, for when an F naught is constant, okay, here if you change the F naught, obviously you can increase the power a lot better. Okay, if you change the force, if you run the motor harder, then you can supply a lot of power within a small amount of time. Sure, but if you keep the F naught constant, okay, the amount of power that goes into the system depends on the acceptance of the system. Does it make sense? If the system doesn't want to accept, then you're not dissipating, you're not doing any, you're not changing any, you're not supplying any power. Let's go for the ridiculously high limit of R. R tends to infinity. Okay, so you have an electron that is tied to that is doing a simple harmonic oscillation around. Okay, let's say the electrons are, let's not talk about electron. Let's talk about a block. Okay, let's talk about a block, and let's say this friction is extremely high. Okay, and you supply an external force, some external force F naught. Okay, will you be able to move this block when R is extremely high?
No, sir.
No.
No,
So
sir.
obviously the velocity is 0, right? So the power supplied would be 0, right? Because the block doesn't want to accept. Okay. So the power supplied depends on whether the system wants to accept it or not. And that is why you have, if you're going to go into electrical engineering, you will have something called an impedance matching. Okay.
So then we should name it as power absorbed, not power supplied to the system.
Power. Yeah. Sorry. Power absorbed. Oh, you're right. Yeah.
Here power supplied is the amount of power that is being accepted by the system, not being the supplied to the system. Am I right?
I should have used power accepted, maybe not power supplied. That's probably what caused all this mess, right? Yeah,
Yes.
it's a good suggestion. Yeah, I can say that it's power accepted. Okay. Yeah, maybe not power supplied. It's a wrong use of the term. Okay. Maybe you're right. Maybe that's where the confusion came from. Okay. So it's accepted power. How much power is accepted? Yes. Okay. So power supplied. Yeah. Now I understand why the whole confusion came about. Okay. Supplied power is independent of system. Yeah. I agree. Okay. All right. Okay. So you can rename that as power accepted. That's a better term, much better term. Okay. Okay. So I guess that clarifies, the change of term clarifies a lot of doubts. Am I right? Is that okay?
Yes, sir.
Okay.
Yes, sir.
Okay. So P average, which is the power accepted, power, let me write it down, accepted by the SHM is F naught square over ZM cos phi, which is also F naught square over or F naught square over ZM square. Okay. And the next is power dissipated by the system. Okay. What is the power dissipated by the system? That would be the force due to dissipation, which is Rx dot, right? This is the dissipative force. Am I right? R times V. That is what we wrote down in your damped simple harmonic oscillator term. Remember?
Yes, sir.
Okay.
Yes.
So this is the force due to dissipation, and the power dissipated would be Rx dot times X dot. That force times the velocity, right? Yeah.
Yes, sir.
Okay. So you can do the same calculation by substituting for X dot and doing the integration. So P dissipated equals, this is average, by the way, 1 over T, 0 to T, F naught square over, so there is an R, and velocity, well, let me write it separately. R F naught square over ZM square cos square omega t minus phi dt. Am I right? So R X dot square. This is X dot square. This is R. Okay.
Yes, sir.
Okay. So if you do this, the power dissipated obviously is going to be the same as before, right? F naught square over 2ZM cos phi, which is the same as power. Power. I keep saying power supplied, maybe power accepted. Okay. Does it make sense?
Yes, sir.
Yes, sir. Yes,
So
sir.
it's simple. I tried to do this. I could have just told you guys the power dissipated is power accepted. It's obvious, no questions asked. But we are going to use these terms in defining the Q factor. Okay. Now Q factor is related to bandwidth of the resonance curve. What? Are you crashing now? Yep, I did. Hold on, let me get it back. Okay, I think I lost the page. Okay, so Q factor again is related to the bandwidth of the resonance curve. I'm sorry, my handwriting is really abominable. Anyway, I hope you guys can understand, can read my words, my writing, right?
Yes, sir.
Yes, sir.
Yes.
Okay, so you have the velocity resonance. Okay, let's in the velocity resonance case, let's do the power. Okay, the power changes as you change omega. Okay, the power supplied becomes maximal when the velocity is maximal, right? Right, because obviously when you define power, it's F dot V, right? So when V is maximal, P is maximal, right? So you have a similar curve, like we've drawn something similar for velocity. It's going to be very similar for power as well. Am I right?
Yes, sir.
Okay. At a specific frequency, which is omega equals square root of m, omega naught equals that. At this particular frequency, the power accepted is going to be maximum.
Yes, sir.
Okay. And how much would that be? What is this value? Okay. The power, we wrote down power supplied is F naught square over Zm or Zm squared. Okay. When it is maximal, omega naught is S over M. And what happens to Zm there? Zm becomes?
It will
R, only R, sir.
Exactly. Zm becomes R.
be R
So
will be
Zm squared is R squared. So it's an F naught squared over R. Yeah. There has to be a factor of 2 somewhere here. Yeah, it's F naught squared over 2m. 2m Z naught. That has to be a factor of 2. Did I use the factor elsewhere or no? Maybe that was a mistake in previous.
Yes, sir. That was a
Yeah,
mistake.
there is a 2 here. Yeah.
Yes, there was a 200.
Yeah. So there is a 2 here. So F naught squared over 2R. That is your maximum value. F naught squared over 2R. That is your maximum power delivered. Okay. Now we have to define what a bandwidth is. Okay. Let me draw that again. This is P. This is my curve. This is omega. Okay. This is your maximal P, which is F naught square over 2R. I guess you guys understand what this curve is, right? So what this curve means, let me explain it again. What this curve means is that you have an externally supplied force which oscillates with a certain frequency omega. Let's say cos omega t. This is my force, externally supplied force. Let's say this is an electromagnetic wave impinging on an electron. The electron is going to do a simple harmonic oscillation. Okay, let's say this is the force that you're supplying to the electron. The electron has its own frequency, omega naught equals square root of S over m, depending upon how tightly it is bound to the atom, to the nucleus. Okay. All right. So if you keep changing the omega, okay, from low values to high values, okay, the power supplied by this external force, by this electromagnetic wave to the electron changes. And it will be maximal when the omega here, the oscillation frequency of the electromagnetic wave matches the natural frequency of the electron. That is when this maximum thing happens. All right, so the power absorption happens when the natural frequency of the oscillation of the electron in the atom and the frequency of the electromagnetic wave supplied from outside matches. Okay, you can think of this as microwave, and this is electron in water, H2O, and this would become a microwave oven. Okay, and microwave ovens operate in a resonance regime, obviously, because you need to supply a lot of power to the water molecules to heat them. Okay, so this is where you would operate. This regime is where you would operate your instrument to supply maximal power to the system. Okay, now what is the bandwidth? The bandwidth is defined like this. You take half of the power. This is maximal power. You take half of that maximal power, which is F naught square over 4R. Take the half of that power, and then you draw these drop down these lines from the intersection point to the x-axis. So this is omega 1, you call this is omega 2. This omega 1 and omega 2 minus omega 1 is a bandwidth. Does that make sense?
Yes, sir.
Okay, you cut the graph in half, basically half of the maximum value, and then drop these lines down, I have to say, to the x-axis, and find where these frequencies are, and the difference between these frequencies would be the bandwidth. All right.
So we are cutting it half because cos square average value is half.
Cos square, what?
So why we are cutting it half? Like
you can cut it anywhere. You can cut it anywhere. Basically, it's an easy definition. You can the average of cos square is half. That could be a valid reason, yes. But it's a way of defining. It's just a way of measuring something, right?
okay.
This way of measuring the width. So where do you want to measure the width, right? You can measure the width at 1/4 or 1/8, whatever. 1/2, as you said, is possibly because the integral of cos square is over one cycle is half. It could be one of the reasons. Yes. Yeah, makes it easy. Sure. Okay, but this is a measure of the width. That's it. You can define it in whichever way you want, and this is probably the convenient way.
Yes, sir.
Okay. So omega 2 minus omega 1 is the bandwidth. That's defined as the bandwidth. Now, if you take, let's say you have a radio, you want the bandwidth to be large or small?
It should be small.
It has to be small. Yeah, because you don't want interference. Okay, from other channels. Let's say you have a channel here, you have a channel here, and you have a channel here, right? If your bandwidth is large, all those channels are going to be picked up. Okay, and in a microwave oven, you don't, again, you want a very sharp resonance. You don't want a broad resonance. Okay, you want a reasonably sharp resonance. Okay, if you have a broad resonance, what happens is the electrons in other molecules start vibrating as well, and you don't want that. Okay, you don't want to burn the food. You want to just heat the food through water. Okay, so it's good to reduce the bandwidth. Okay, and think about the quality factor. Think about what a quality factor is. Okay, if you want the machine to work well over many cycles, like if you want to work if you want the refrigerator to work over many cycles, if you want your AC to work over many cycles, your Q factor should be large or small?
Large, sir.
It should be large.
Yeah,
I'm sorry. Yeah, if your Q factor. Yeah, go ahead.
So then, like, if you are telling that the Q factor should be large for a good device, and in the bandwidth, the definition is like only for P power by 2, or we can take some other values also.
You can take whatever value, but it becomes easy to it becomes easy to calculate with half. With the definition of half, it becomes easy to calculate. We will see that it becomes much easier to calculate Q factor using the definition that at half of the power, you define the bandwidth. It becomes much easier. Okay. Okay. So if you want a device to operate over many cycles without much dissipation, okay, you want high Q factor. All right. Here, what we've been arguing is like if you want a microwave oven, if you want a radio, if you want an antenna, or whatever device that you have, if you want them to operate well, then you want the resonance to be sharp, which means you want the bandwidth to be small. Does it make sense?
Yes, sir.
Okay, so large Q factor should be related to this to small bandwidth. Does that make sense?
Yes, sir.
Does it make sense?
Yes.
Yeah, if you want a microwave to work well, you want the bandwidth to be small. Okay, so the way Q factor is defined is this: omega naught over omega 2 minus omega 1. The bandwidth goes in the denominator. Okay. So the
Yes, sir.
smaller, I'm sorry.
Yes, sir.
Yeah, the smaller the bandwidth, the larger the Q factor. Okay, so this is another definition of Q factor, the third definition. There is also another definition, which is as an amplification factor. Q factor as an amplification factor. I'm not going to go into that. Okay, but this is the third definition of Q quality factor.
So one explanation of why the value of omega 2 and omega 1 is related to P max by 2 can be like we have another values of Q factor also. So to match the both values, we are taking the omega 2 and omega 1 at that specific point. Can we set this?
Yes.
Can we set this also?
Yeah, exactly. Yes. Yeah. Exactly. As it's all related to, as one of you pointed out, it's all related to cos squared theta d theta equals a half. Okay, it's related to this. Okay. However you define your bandwidth, you're going to match it up. That if you define the bandwidth as 1 over 1/4 of P average, then there will be some factor here. There is some alpha factor here. You'll have to multiply that factor here. Okay, but if you don't want to have any factor here, then you better define this as a half of the P average. Yes.
So half is a reference point. Like
Yes, half is a reference point. It's not arbitrary. There is a reason for half, but you can have any factor. If you want to define a bandwidth, you can have 1/4 of the average value or 1/8 of the average value. You can do any of that, but half makes your calculations much simpler. Okay. Does it make sense?
So for other than half, we need to put an alpha to satisfy our equation.
Yeah. You need to have some constant. You have to multiply that by some constant. Okay. So can we find what is omega 1 and omega 2? What is omega 1 and omega 2? Given that P average maximum is f0 square over 2r. Okay. Given this, what would be and we know that P average is f0 square over 2 ZM cos phi. We know this. Okay, we know this. Can we find this? Can we find omega 1 and omega 2? Okay, let's try. F0 square, this is P average. F0 square over 2 ZM. Let's, instead of cos phi, I'm writing this as R over ZM. Cos phi as R over ZM. That's okay, right? Okay, and
Yes.
This must be equal to half of maximum power. half of maximum power, okay, which is half of f naught square over 2r. Am I right?
Yes, sir.
Yeah. So you can just equate this r over f1 square over 2 gm square equals f naught square over 4r. Okay. So if you just equate this, you can do this r comes over here, which means gm square equals r square. That is a 2r square. Right? That's a condition. For finding where omega 1 and omega 2 are. Yeah, I'm just equating this, equating the denominators. The r goes over here. Yes or no? This is a condition.
Yes.
To find where omega 1 and omega 2 are. Okay, so this is r square plus omega m minus s over omega v equals 2r squared. Okay. Oh, sorry, this is squared. Yeah. Are you guys confused, or I don't?
No, sir. It's quite
You're-
clear.
you're-
We have studied this type of
So now-
equation in class 12th also in alternating current chapter.
Okay. Okay.
Yes, sir.
You're not. This is not new to you. Okay. Good. Good. So omega m minus s over omega equals square equals r squared. So omega m minus s over omega equals plus or minus r. Right? So one of these roots will give you omega 1 and one of the other roots will give you omega 2. Okay, so let's say omega 2 m minus s over omega 2 equals plus r. Omega 2 is larger than, let's say, then omega 1 m minus s over omega 1 equals minus r. Right? So from these two equations, you can find omega 1 and omega 2. Or you can find omega 2 minus omega 1. You can just solve them. It's pretty easy. Okay, you multiply omega 2 here, omega 1 here, and do that. It's pretty simple calculation. And when you find, what you find is omega 2 minus omega 1 equals r over m. Okay. Okay, so the bandwidth is very simply just r over m. If you increase the resistance, you increase the bandwidth.
Sir,
Mm-hmm.
so like in the first and the second equation in terms of omega and omega 2, like there will be 2 omega 2 and there will be 2
Omega
omega 1,
1.
right?
Yeah, sorry. Yeah, you're right. I made that. Thank you. Yeah, it's omega 1. Okay. Okay.
So one thing we can also do is like when we solve the equation for omega, it will come like omega square m plus minus r m omega minus s is equal to 0. So we'll be getting the same value of omega 1 and omega 2 from that equation also. So from the second equation from the top.
Yeah. Okay.
So if
Yes.
second equation from the top will be getting the same value as we get as solving omega 2 and omega 1 differently.
Yeah, you can follow whichever way you like, right? The easiest way is perhaps this. Okay, here you're not even solving the quadratic equation, right? What you're doing here is not, you're not even solving the quadratic equation. It's pretty simple here. Okay, you want me to solve this?
No, sir, it's okay.
Yeah, all that you have to do is to multiply this omega 2 square, and then here you have omega 2, and this goes off, and omega 1 square, omega 1, and then you subtract both. That's it. Okay, the omega 1 plus omega 2 cancels off. Okay, so you're not even solving the quadratic equation here. It's very simple. Okay. Anyway, let's get down to the physics part of it, where you see that the bandwidth is proportional to R. Okay, it's a neat result, because you know, the more the resistance, the higher the bandwidth. Okay, it kind of makes intuitive sense, right? It is the resistance part that introduces the bandwidth. If there is no resistance, the bandwidth would be very sharp. The bandwidth would be very small, and the resonance curve would be very sharp. Okay. Okay.
Yes, sir.
Yes, sir.
So this is used
Yes.
in physics quite a lot. So let's say let's say you have an atom. Let's say you have an atom with an electron bound to the atom. Okay, you shine it with some light of varying frequency omega. Okay, and you take a spectrometer and you observe how much light has been scattered or absorbed. You can, either one of them is same. It's scattered or absorbed. They are, if you can measure absorption spectroscopy, you can do also emission spectroscopy. It's both similar, both the same thing. So let's look at the absorption. How much wave has been absorbed by the atom? Okay, so for by varying frequencies. So let's say this is 1, which means no absorption. Okay, all the light passes through, and at some frequency the atom absorbs. Okay, some omega naught the atom absorbs, and after that nothing. Okay, so you know the resonance frequency of that particular atom. Okay, of the electrons in that particular atom, you know that. Okay, and this curve is usually extremely sharp. What does that mean? Is that the atom is not dissipating so much. Does it make sense? Because the bandwidth is really small. Does it make sense or not?
Yes, sir.
Okay, do interrupt me if you don't understand what I'm talking about. Okay, so now you take the same atom and you put that atom inside a crystal. Okay, there are other atoms bonded to it. Okay, and now do the same operation. Okay, shine some light on it and see how much light has been absorbed. Okay, now you look at the spectrum. You will see that the spectrum has done that. Okay, you have a width. You have some resistance. Okay, why is that?
Is it like due to the restricted movement of the atom in the crystal?
That is, you can say that. You certainly can say that. Okay. Okay. There are many vibrational states available within the single atom. There is only one vibrational state available, and that's why you have this. When you put that in the crystal, there can be many possibilities of the atom vibrating, of the electron vibrating. It can vibrate here, it can vibrate along this one, and the other electrons are also going to influence the electron's vibration. So there are many possible ways or many possible frequencies of vibration for the same electron. Here the electron is it's in a pure environment. Here it's in a mixed environment, so there can be a lot of frequencies imposed on that particular electron. Okay, so the electron will vibrate in many possible frequencies. I wouldn't say like I would draw that. That's a wrong suggestion. But depending upon the environment, the electron is going to vibrate in many possible frequencies, not just one. Okay, there will be many frequencies possible, and that's why you have the broadening. Okay, so depending upon the environment, you will see how much you will see the electron has the absorption has broadened.
So will there any peak in the second graph? Like in the first graph, we are having a peak. So
Yes.
for the second graph also, will there be any peak of the
There will
omega?
be, yeah, there will be peaks if you look at the core electrons. Like there are valence electrons, and if you take the core electron, not here, you even here you will see a lot of sharp peaks. Not one, many peaks depending upon all the electrons. Like the core electrons will create a sharp peak, and the valence electrons will also create a sharp peak here. But here, the core electrons will create a sharp peak, but the valence electrons will create a broad peak, because the valence electrons are going to be affected very much by the environment of the crystal. The core electrons will not be affected so much. So we will still get a sharp peak here. Does it make sense?
Yes, sir.
Okay. So just by looking at how broad these peaks are, you can really figure out the type of the environment that the atom is in, the type of the crystal that the atom is in. Okay, this is similar to NMR spectroscopy, nuclear magnetic resonance spectroscopy. They look at broadening. Okay, so this bandwidth behavior, this bandwidth picture is very important for physics, particularly in spectroscopy. Okay, how these lines are broadening. Okay, and just by looking at the lines, broadening of the lines, you can figure out something about the environment of the molecule. What environment the molecule is in. You can imagine that, and this is for a crystal that you have in your hand. Remember, this light comes from a star or from an extrasolar planet. Okay, there you don't know what kind of behavior, what kind of neighborhoods, what kind of crystals that the atoms are in. Okay, you will get some kind of a spectrum. You will get a hydrogen spectrum, let's say. Okay, you will get all those lines. I'm sorry.
So one doubt.
Uh-huh.
So that may be not related to this thing, but when we talk about core electrons, we assume that core electrons are stable generally in all the elements. But if we go into the radioactive elements, like in the case of nuclear fusion and chain reaction, the core electrons are not that stable, not that their case is same as the valence electron in the stable element. So in that case also, there will be some peak or sharp edges in the graph.
Actually, the statement that core electrons are not stable in radioactive elements is not quite true. Okay, they are mostly stable, but sometimes what happens is there is an emission of alpha particle or a beta particle from the nucleus, and that knocks out the core electrons. Okay, and that's when the core electrons get destabilized. So there will be a small broadening, but that will be very very small. It will be nearly invisible. Okay. Okay, those are called Auger electrons. You might have studied that, right? But it wouldn't create much of a broadening. Okay, it would be nearly imperceptible. Okay, they would still be, you can still think of them as quite stable. Okay, unless you're looking at radioactive atoms that have a lifetime of let's say half a microsecond. Okay, if in that case, yes, most electrons are going to be unstable. But for many radioactive elements, which are like of the order of days or years or decades, there the electrons are going to be very stable, and you will not see any you will not see any broadening. Okay.
Okay, sir.
Okay. Okay. So if for light coming from an extrasolar planet, these broadenings are extremely important. Okay. The broadening tells you a lot about the environment that these molecules are in, like particularly hydrogen atom. Right? If the lines are broadened, then you know that the hydrogen atoms are not free. They are bonded to something. Okay, and depending upon how much the broadening is, you can qualitatively figure out where they are bonded to which molecules they are bonded to. Okay, and you can figure out if it is a carbon molecule, if it's a carbon atom, if it's an oxygen atom, whatever. Okay, let's say if you figure out just by looking at the shift in the frequencies of oscillation of the hydrogen atom electrons, if they shifted slightly such that you can actually figure out if it is bonded to O2, if the hydrogen atom is bonded to oxygen. That would be revolutionary. That would be like finding water on an extrasolar planet, right? Just by observing absorption spectra of hydrogen atoms. That's it. That's all you're doing. Do you understand how important broadening is? Broadening and shifting of frequencies. Okay, these are enormously important in spectroscopy. Okay, anyway, I don't want to go much further into that. So Q naught is omega 2 minus omega 1, which is omega naught R over M. No, omega naught M over R, sorry. Okay, and this is the same thing that we found out earlier, right? Yeah, omega prime, we derived omega prime M over R. Remember this? Okay.
Yes.
Yeah. Okay.
Yes, sir, by energy method. Like
Yeah. Yeah. So omega prime, you guys remember omega prime is omega naught square minus R over square over M square, something like that. When R is small, this can go to that. Okay.
Yes.
Okay. Okay, so we will stop here for the quality factor part. That's basically it, and I'm moving on to another. We're gearing up to the next level. Okay, I'll stop for this one. Okay. You guys want a 5-minute break, or can we carry on? Anybody?
So we'll take a 5-minute break maybe.
Okay. Okay.
Yes, sir.
Okay. Yeah. Hi guys.
Hello, sir.
Hi.
Yes, sir.
Yes,
Oh,
sir.
yeah. Can we start or?
Yes, sir.
Yes, sir, we can.
Yes, sir. Resume.
Okay. 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 Let's switch gears. Okay. So far we have looked at simple harmonic motion, right? And we looked at it because it underlies many other phenomena in physics. Okay. The most important of which is waves. Okay. So you can think of waves as a collection of particles doing simple harmonic motion. That's it, right? They are connected to each other. Each of these particles is connected to each other and doing simple harmonic oscillation. All right. So that is one of the reasons why we spent so much time in simple harmonic motion, right? But we come to the more meatier part of the syllabus. Okay, waves are a lot more interesting. Okay, we will be looking at linear waves, linear equations. Okay, there are also non-linear waves. Okay, those are way much more interesting than linear waves because obviously non-linear waves behave in a weird way. Okay, there are things called solitons. Have you guys heard of that? Solitons. Okay, these are
No,
waves
sir.
that travel without any dissipation of energy for very long distances, miles and miles and miles. Okay, these have been observed in canals near a place where I lived a long time ago. That was where the first time they observed the solitons. And there's also rogue waves in the ocean. Okay, these are waves maybe 30, 40 meters tall, 30 to 40 meters tall, even more sometimes. Okay, and they come out of the blue, basically. No trigger, nothing. Calm seas, everything is fine. Somewhere far away, there is a storm brewing, and you get this rogue wave. Okay, these are huge waves that can topple ships. Okay, and this is also nonlinear waves. These are nonlinear behaviors. We're not going to be looking at them, but they are way much more interesting, obviously. Okay, we'll be looking at linear waves basically, which obey linear equations. Okay.
So in non-linear mathematics of linear waves will be applicable or not? Like superposition and all those things. Will
No,
that be?
no. Yeah, no. Good question. In nonlinearity, you don't have superposition. So what happens is in nonlinearity, let's say you have a wave with an amplitude A1 comes and a wave with an amplitude A2 comes. Superposition says A1 plus A2. Okay. The total amplitude can be maximum that much. But with nonlinearity, the total amplitude can be this. Okay, you have an amplitude of A1, you have an amplitude of A2, but because of nonlinearity, if there is a square term in your equation, then your amplitude can be that. Or your amplitude can be this. Okay, it can be anything. So the superposition principle does not hold. Okay, and that's when things get very interesting in nonlinearity. Okay, but we have to first study the linear waves to understand nonlinear waves. Okay, you cannot just right away jump into nonlinear physics because you need to know the fundamentals before we go on to go to higher topics. Okay, So I'm not going to be talking about nonlinear physics. I mean, not even master students have the courses that talk about nonlinearity. Okay, nonlinearity is purely reserved for research for now. Okay, so you will not have any courses that talk about nonlinear waves, right? Not even at the master's level, only at the research level. Okay, I'm telling this to you guys because there is so much physics out there that people are doing research on. Okay, that you wouldn't even be aware of. Okay, so that's way much more interesting. I just want to kindle your interest. That's it. Okay. Okay. So let's talk about waves. The first thing we want to get out of the way is speed of waves. Okay. Let's say you have a pond and you throw a stone in the pond and you have this waves propagating from the center to the periphery. What do you think is the speed of the wave? How do you measure the speed of the wave?
Omega by Q.
By how? What is the speed? How do you define the speed of the wave? Anybody?
Change
So we
of
take a
radius.
point and we see.
Change of radius. And what else?
So like in practical terms, we take a point and we see when the next trough or next crest will come
Okay, you take a
and
point
divide
and the wave is
and
moving.
So we take
uh,
see the point t and then t minus x by v.
Don't go to mathematics. Okay, don't go to mathematics. Intuitively. Intuitively, how do you define? Somebody said expansion of radius. That's a good suggestion. How the radius expands. Okay, but what do you really mean by radius here? What is radius? What are you defining there? How do you draw a circle? Circle of what?
Crusts, sir, crusts.
Crests. Okay. Okay. So you're saying how the crest moves through the space. Is that what you're saying?
Yes, sir.
Yes, sir.
So the velocity of a crest or a trough, right? How much? So basically, this is a wave, and this wave is moving with time. So this is a time t. This is a time t plus delta t. The crest has moved a little bit. The trough has moved a little bit, right? So how much the crest has traveled in the time delta t, that defines the velocity. Are you saying that? You don't have to, there is nothing wrong or right. You just, use your intuition. You don't have to feel bad about being wrong. I mean, students cannot be wrong. It's just that they haven't learned.
Sir, can we use change in area between two successive crests?
Change in, where is the area here?
Between two successive crests.
Two successive crests, like
Yes.
this and this.
Yes.
But this is going to be a constant, right? The wavelength will be a constant of a wave, right? Okay, any ideas?
So in intuition term or not, I'm not exactly sure, but the rapidness, we define the speed by rapidness with the space is being traveled by a wave. Like the rapidness with a wave which covering the some space can be defined as speed.
Yeah,
In
but how do you quantify that?
Otherwise, can we say like that? Like if we know the wavelength of the wave, like we can say how many crests pass through that particular length in 1 second.
Okay, so you're just using c equals nu lambda. Okay, we're not even going there. I don't want to have c equals nu lambda. I don't know what c equals nu lambda is, let's say. Okay, I don't need to use that. It's an intuitive thing, right? You know, how fast something is traveling is quite intuitive. Am I right? Okay, so the easiest thing is what somebody told before. It's a velocity of a crest point.
So, but how we are defining fast? Like if we define the speed of light, a bullet train fast, but compared to the speed of light, the speed of bullet train is negligible. So the fast and slow is a relative term. Like we have to define a relation, like
Okay,
with what respect that thing is fast.
so that is up to you to define, right? You look at a wave. Is the wave moving? You look at a water wave. Is the wave moving? Yes or no?
Sir,
Hmm?
sir,
Mm-hmm.
I have a doubt. Like, just imagine we keep that thermocol ball in the pond, and we throw a stone, and a ripple is created. So the
Mm-hmm.
thermocol ball will oscillate, and
Mm-hmm.
since the thermocol ball is very light, we can accept that it's very much attached to that water particles, and we can assume that the oscillation of the particle is same as the oscillation of thermocol ball. Okay, so the
Okay.
thermocol ball will have an oscillation.
Mm-hmm.
So the speed at which thermocol oscillates and the speed at which the wave is traveling, is that same?
Okay. Okay. Good. Good. Very good. You're going somewhere. Okay. You're going somewhere. Do you
Is that
think the
same?
thermocol? But do you think the movement of the thermocol is associated the? So again, let's go back to the question. What do you mean by the wave is moving? What do you mean by that?
So coming to one point, I also want to add.
Mm.
So speed is a term, something that is defined as a frame of reference. Like wave is traveling and we are on that wave only. Like I'm assuming that I'm particle, I'm sitting on that wave only. So for me, that wave is stationary.
No,
So
I don't want to go to relativity. I will say that you're standing on the side of the pond, or side of the canal. Let's say there is a canal. There is a water wave that goes through the canal. You're standing right by side. You're standing still. You're not riding along with the wave. Okay, so the wave is moving. Okay, you know that the wave is moving, right? When you observe a wave, you know that the wave is moving. Am I right? It's not still. It's not
so
a standing.
assuming, so assuming we are not standing on the wave, we are assuming we are outside
Yeah,
of the
yeah.
wave.
Assuming we are outside, obviously. We are outside, standing outside the wave. The wave is moving. Am I right?
Yes, sir.
Yeah. So if it is moving, it has a velocity, right? Right? Is that velocity
Yes.
the same as the thermocol velocity that the other person was talking about? Is this the same as this thermocol velocity? The
No,
thermocol
sir.
is moving up and
No,
down. No, it's not. Right? Because the thermocol is not moving in this direction. Thermocol is moving in the perpendicular direction. So the thermocol velocity is a particle velocity. It's called particle velocity. It's a good point, but it is a particle velocity. It is not the wave velocity. It is the particle that that forms the substrate for the wave to move through. Those particles are moving as well, and that is the particle velocity. Okay.
So, but the frequency would be same.
Yes, the frequency is the same. The frequency of the wave and the particle would be the same. Exactly. Yes. Yes. But the velocities don't have to be the same.
Yes, sir.
Okay. The wave velocity, the wave can move really, really slowly, but the particle can move fast. Okay, whatever. What I'm saying is that the particle is moving in the perpendicular direction and the wave is moving in the, let's say the particle is moving in y direction and the wave is moving in x direction. So these two velocities cannot be the same. So what is wave velocity? Okay, the simplest explanation is very simple. I mean, you guys already know this. Okay, so you have a wave. This is at time t. You have
So
the
it's
same
simply
wave
lambda
uh, at time t
by
equals
time period.
to delta t. I'm sorry.
It's simply wave divided by time period.
No, I'm trying to intuitively understand what you say. So basically, the crest is going to move through the space. Okay, the crest is moving from this point to this point. Okay, so this is delta x, right? The crest has moved a certain distance after a certain time, delta t, right?
Yes, sir.
How fast the crest is moving is your wave velocity, delta x by delta t, as delta t tends to 0. That is your velocity. How fast the crest is moving forward. Or you can equivalently define how fast the trough is moving. The same thing. It's intuitively obvious, right?
Yes, sir.
This is what you would define as the wave moving. The wave is moving because you see the ripples moving outward. So if this is the ripple, after some time the ripple has moved forward. If this is your origin where you drop the stone, after some time the ripple has moved outside. Okay, and the ripple has moved by a distance delta x or delta r or whatever. Isn't that obvious? Is this
Yes,
intuitive or no?
yes, sir, it's intuitive.
Okay. It's pretty intuitive.
Yes.
Okay, this is how you define the velocity. Velocity is the speed at which the phase of the wave travels. This is your phase. This is phase phi equals let's say 0. This is phi equals pi by 2. Phi equals pi. Okay, this is phi equals pi by 2. That's the phase. This is phi equals 0, let's say. Okay, this is again phi equals 2 pi. Okay, so the phase moves at a certain velocity. Right, the phase phi equals 0 moves at a certain velocity. You can take phi equals 0, or you can take phi equals 2 pi by 2, phi equals pi, whatever phase you choose, you follow that phase, okay, through the axis, through the space. Okay, how fast that phase is moving, okay, and that is your wave's velocity. Am I right? Am I right?
Yes, sir.
Okay, so you have particle velocity, which we looked at, the velocity of the thermocol, as someone explained. Okay, you have particle velocity and you have phase velocity. Okay, you have phase velocity,
Sir,
and this.
now you said like the particle velocity can be very fast and the wave velocity cannot be that fast or can be slow. Sir, sorry, but I can't recall any case. Can you help me with that? I can't recall, like the particle velocity is very fast and the wave velocity is slow. Is there any case like that possible?
Yeah, sure. So let's say you have a guitar string. You have a guitar string. Okay, the guitar string oscillates like this. It's pegged at the ends. Okay, so your thermocol particle is attached to this point, let's say. Okay, it's going up and down and up and down. But what is the velocity of the wave of the string? It's a standing wave.
0, sir.
It's 0. But the particle is oscillating. The particle velocity is non-zero. Yeah?
Yes, sir.
Okay. So your wave velocity is not related to the particle velocity. The particle velocity here is very, very high, actually. Okay. Whereas the velocity of the wave is 0. It's not going anywhere. It's a standing wave. Okay. So the phase velocity of this wave is 0. Okay. Okay.
So, sir, can we say that the velocity of the particle will depend on the velocity of the wave as well as the slope?
Mm, uh, the velocity, it does not depend on the slope. The velocity of the particle depends on the frequency of the wave, that's omega of the wave, okay, and the amplitude of the wave. Okay, the particle velocity is basically particle velocity is basically A sine omega t or something like that. Okay, A is the
So, but
amplitude.
like, can we say like, suppose x is equal to a sine omega t minus kx for some wave executing SHM. So, velocity of the particle will be that dx by dt, and then slope will be again dy by dx. And if we divide those two equations, we will get like Vp, the velocity of
That is
particle is
that.
equal to minus v of wave into slope.
Yeah, yeah. That was wave velocity. You are telling me that was
Okay,
wave
so
velocity. Which
yeah, when you take a slope, what you do is you're connecting it to a neighboring particle. Okay, we are looking at just a single particle, so slope cannot be a function. Your velocity cannot be a function of the slope. You understand that?
sir, one doubt, sir.
Yeah.
So particle velocity would be a omega sine omega t, no? So
Oh,
that
sorry.
the maximum.
Yeah, sorry. Yeah, it's A omega sine. Yeah, thank you. Yeah. Okay. So basically, the maximum velocity would be just omega A. Okay. It does not depend on the neighboring particle, so it does not depend on the slope. If your particle velocity depends on the slope of the wave, then the particle is basically connected to a neighboring particle, and the neighboring particle determines the velocity of this particle. Okay, that is usually not the case, right? I wouldn't say usually not the case,
Yes,
but
sir.
the particle velocity is independent of the slope. That's what I'm saying. Okay.
Yes, sir.
Okay. 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 We can think about it, but I don't want to go any deeper because we have much to cover. Unfortunately, the pressure of syllabus takes away time for in-depth, intuitive understanding. Unfortunately, we cannot escape that. Yeah. Yeah. If it was a single class instead of 10 classes, instead of 10 sections, if it was a single class, then I can decide what to cover and what not to cover. Okay, basically that's what I do for my master's courses. I decide what to cover and what not to cover, and I can cover some topics much deeper, and then leave out the rest of the topics that I think are can be absorbed later. Okay, but in your case, in your class, I cannot do that, unfortunately, because we have 9 other batches, and the exams will be centrally organized, which means the questions are going to be given by many other faculty. So I have to cover all the subjects, all the topics. I cannot leave out topics. Okay.
Yes, sir.
Okay. And for that, I need to rush through, unfortunately. Okay. How much ever I wish to cover something deeply, okay, I cannot do that. I
So
try to.
uh, can you just keep extra classes like we can discuss in those
Let's
classes?
see. I don't want to also stress out too much. I don't want to stress you guys too much also. Yeah, I want to take it light and easy. Okay. 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 Let's see. If you guys are very interested in, I know the quantum mechanics is going to be quite interesting. So let's hope we'll have some time for that. Okay. And if not, we'll have extra classes. Okay. We'll talk about that. Okay, so particle velocity is the velocity of the particle that is oscillating. Phase velocity is the velocity of the phase. It's the speed at which the crest or trough is moving. Okay, and then there is something called a group velocity. Okay, this is not a very intuitive concept. Okay, what is this group velocity? Have you guys studied about this? Did you guys
No, sir.
not
No, sir.
in your class too?
So we have
No,
studied
sir.
about
No, sir.
particle velocity and wave velocity, not about the group velocity.
Yes, sir. We have not studied that.
Okay. Okay, so let me then start simply. Let's say you have two waves, x equals a sine omega 1 t, and so let's say x1, x2 equals a sine omega 2t. Okay, and let's say this omega 1 and omega 2 are really close to each other. Those frequencies are really close. Okay, so what would you have? What kind of so x is x1 plus x2 is the behavior. What kind of behavior do you see of these waves, these oscillators?
Sir, like a beat formation.
It is a beat, exactly. Okay, it is a beat, something like this. So you have something like this. Okay, and this frequency is omega 1 plus omega 2 over 2. And what is the frequency of this envelope?
So the difference by 2, half of the difference.
Omega 2 minus omega 1 over 2. That's a half of the difference.
So this is AM, amplitude modulation.
Hmm? Yeah,
So amplitude modulation.
it is similar to amplitude modulation. Yes, it is similar to amplitude modulation. Now the question is, there are two phases here. One is the phase of this wave, the wave, the carrier wave. It's called okay. You can call this a carrier wave. Okay, this carrier wave. This has a phase and this has a velocity, and you have this envelope, and the envelope also moves. That has a velocity. There are two different velocities, right?
Yes, sir.
So this is phase velocity, and this is group velocity. Okay, the group velocity is the velocity of the group of waves. You are basically combining two waves here. You can combine many waves, many waves, and then you look at the envelope of those combination of the waves and see how that envelope moves. And that envelope can move at a different velocity compared to the rest of the waves. If all the waves that you're adding have the same velocity, then the envelope will also have the same velocity, obviously. But if all the waves that you're adding have different velocities, then the group velocity can be different. Okay. So group velocity is the velocity of a group of waves. Okay, and this group of waves can travel at a different velocity compared to the constituent waves, the velocity of the constituent waves. Does that make sense?
Yes, sir.
Okay, so so Vg, that's group velocity. You can think of that as omega 2 minus omega 1 divided by k2 minus k1, where k is 2 pi over lambda. Okay, so there are two different lambdas and two different frequencies, omega 1 and omega 2, and there are two different lambdas for those two waves. Okay, then there are two different velocities. The first velocity of the first wave is omega 1 over k1. Velocity of the second wave is omega 2 over k2. Okay, so there are two different velocities. Now the group velocity is defined as omega 2 minus omega 1 divided by k2 minus k1. That is my group velocity. Okay, and if you have many waves with slightly varying omega, then you would say d omega by dk. Okay, this is approximately the same as omega 2 minus omega 1 divided by k2 minus k1. Sorry. Why am I doing this? Go away. Come on. Okay. Okay, so this is my group velocity. Group velocity is the velocity of a group of waves, the phase velocity of a group of waves. Okay. Does it make sense?
Sir, can you please give the physical significance of group velocity? Like, I'm not exactly able to recall the topics where I can use the VG and everything.
Okay. Good question. Let me can't. In deep physics, there are a lot of group velocities, but in fundamental physics, Okay, so let's take a slab of a slab of glass. Okay, let's take a slab of glass. Let's pass white light through that. All right. Now let me ask you guys: would the velocity of the red light be different from the velocity of the blue light inside the glass?
Yes, sir.
It'll obviously be different, right? Yes?
Yes, sir, because the refractive index for every wavelength will be different.
Absolutely. So the refractive index will be different. So there'll be something called a dispersion, right? There'll be something called a dispersion, which means some of the waves would travel faster and some of the wave would travel slower, right? Yes or no? Outside in the free space, the white light, all the waves have the same velocity. The blue light, red light, all the lights have the same velocity. But inside the glass, okay, red light and blue light have a different velocities. Okay, so how would the total light move inside? What is the velocity of the light, total light that is moving inside the glass? Obviously, you're not going to see red and blue separately inside the glass. Okay, it's not a prism. Okay, you're still
So we can
seeing.
take it as speed of the yellow light approximately.
But that is not, I mean, that is for calculational purposes, but what is real velocity?
Sir, velocity of white light upon the refractive index.
Well, no, it's not simple. I'm not asking the answer. I'm not asking the quantitative answer. I'm trying to make you guys understand what a group velocity is. Here, the velocity of the total light that is going through is a group velocity. It is not. It is not c equals 3 to 10 power 8 meters per second. It's not that. No. This Vg is not equal to c. And this Vg is not equal to the velocity of the red light or velocity of the blue light or velocity of the orange light or separately. It's some combination. Yeah. The velocity of the total the waves of all the light waves. Okay, if you add them all, if you add all the waves, let's say you have let's say blue light and you have, let's say, red light. Okay, you add them together, you will see something very different, something like that. I cannot draw it, but the phase velocity of this is different from the phase velocity of these, right? This is blue light and this is red light and this is a composite, this is white light, right? This velocity would be different. This is Vg. Okay.
Okay.
So the velocity of white light inside a glass is group velocity. It's not, if it is this pure red light, then you can easily calculate the velocity. It's just a velocity of the, it's like C over n refractive index for red light. That is it. This is the velocity of the red light. Okay. This is the velocity of the blue light. Right. But for a composite light, it is not as simple as that. You have to add them all together. Okay, and that BVG. That is, does it make sense? Does it make sense?
Yes, sir.
Yes, sir.
Okay. So that's practically that is where you will see group velocity. Okay, waves traveling through any medium. Okay, sound waves Same thing, similar stuff. Okay. And waveguides. Waveguides are extremely important in engineering. So you will see a lot of these examples with waveguides. Okay, their velocities of different waves drastically change depending upon the dimensions of the waveguide. Okay, so there you will use group velocities as well also. Okay, so there are three velocities, particle velocity, phase velocity, and group velocity. Group velocity is the velocity of a group of waves traveling together. Okay, and and let's now get to the description of wave, to the mathematical description of wave. How do you mathematically describe a wave? Mathematical description. Okay, how do you describe mathematically? How do you for any phenomena, the first thing most of the times the first things physicists do is to write down a differential equation. I told you guys that, right? Right?
Yes.
So the question is, what is the differential equation for a wave?
Del square y by del x square is equal to 1 by b square del square y by del t square.
Okay. So what does that mean? What does that physically mean? Is there any physical interpretation for that?
Sir,
When we
it means that wave does not only depend on time but depend on position also.
okay. Anything more? Okay, you're right. Oh, I can write down. I don't have to use psi. X squared equals 1 over c squared dou square y by dou t squared. Okay, this is your wave equation. You guys have encountered this in your +2, right?
Yes, sir.
Yes. Okay. So now that you guys know the wave equation, let me tell you guys how to make sense out of it. How to intuitively understand this equation. Okay, are you guys up for it? Do you guys want to do that?
Yes, sir. From last 2 years, we are just memorizing this equation. So,
Okay.
so
So let me explain what this means. Okay. Now let's first make a wave. Okay. Now we have particles. Okay. These particles are localized. Basically, I'm drawing these beads. These are beads that go up and down within the same pole. Okay. You have a single pole, and the particle just moves up and down. Let's say. Okay. The particle cannot go uh, anywhere else, basically to the sides. It cannot move to the sides. Okay, this is a reasonable picture of a wave, right? What is missing here? What do I have to do to create a wave-like scenario?
So they are group vibration. Like if we look at the vibration of every single particle, they are oscillating in a straight line. But to
Yes.
create a wave, we need to create an combine all the movement of all the particles. Like we need to take a summation of all these movement.
Not summation. Uh, Physically, I'm going to put a spring between them. That's it, right? I'm going to make a spring between them. That's how oscillation happens, right? Every particle is attached to the next particle, right? If this particle oscillates without the spring, if I don't have the spring, then this particle doesn't influence the next particle. It doesn't care. The next particle doesn't care whether this particle oscillates or not. It doesn't care without the spring. You need the spring for propagation of information from one particle to another particle, right? Yes or no?
Yes.
Okay, so you
Yes,
need the
sir.
springs. You need the springs. You need the particles confined to the rod, but you also need the springs. Those are connected to those are connecting the neighboring particles. Okay, now let's take a look at just 3 of those particles. Okay, particle 1, particle 2, particle 3. and there is a spring between them. Okay. Okay. Now, what is the force on this central particle? How does that force depend on the position of these two particles? I mean, think intuitively. Think intuitively. Do not go for mathematics. Do not try to do mathematics.
Sir, if the particle is above both the particles, the particle will experience a downward force, and vice versa. If the particle is below both the particles, particle will experience an upward force.
Very good. Very good. Very good. So I have multiple scenarios. I have this scenario where I'm drawing the lines for the springs. Okay, that is one scenario, and the other scenario is this scenario. Okay, and the other scenario is this scenario. Okay, there are many other scenarios like this. So in which of those scenarios will there be a force? Let's draw the other scenario as well. This is another scenario. Okay, this is another scenario. All these scenarios. Okay, which of these scenarios will there be a force? Let's call this A, B, C, D, and E. Which one?
All except E.
Sir, A and B.
So which part?
And
Which one has the net force? Net force in the perpendicular direction. Okay, in the perpendicular direction, because the particle can oscillate only in the perpendicular direction. So the question is, which of these scenarios have a net force in the perpendicular direction for the particle, for the central particle?
So A and E, A and B. A and
A and B. Good. Okay. C, no. D, no. E, no. Okay. All right. So what is this situation here? So let's call this Y1, Y2, Y3. Sorry. Let's call this X1. Oops. X1, X2, X3, and the position is Y1, Y2, Y3. Okay, so this is Y1, this is Y2, this is Y3. This is Y1, Y2, Y3. Okay, so how do you describe this mathematically? Like, you know that A and B are A and B situations in A and B gives a force, whereas situations in C, D, and E do not provide any force, do not supply force on the central particle. How do you describe that?
Sir, by curvature. If curvature is positive or negative,
Very
then
good.
force will be.
Very good. Exactly. This is curvature. It is curvature. Am I right? If the particles are curved like this, then there is a force on the central particle. If the particles are not curved, if it is straight lines, then there is no force in the vertical direction. Yes or no? Any problem here?
So there may be some cases where there will be a component in the perpendicular direction only, not the whole force is in perpendicular direction. Like I'm assuming in second case, the one component is in parallel direction and one component is in perpendicular direction. So in that case also we will go for curvature or anything else we can do.
So I'm trying to imagine what you're saying. Okay, like you're saying this, right? Is that what you're saying?
No, second ball is also some distance upward, but the force they are putting, the vector sum of that force is not exactly perpendicular to that ball. There is some component that is perpendicular to that ball, and there is some component that is parallel to that ball, like at some angle theta. So both are at some angle, like not there.
Okay.
So the two forces are not equal on the middle. He's trying
So
to
you
say.
have something like this.
Yes, sir.
Yeah. Okay.
Yes.
Okay. Okay. I will answer this question sooner. Okay. For now, we'll ignore these kinks. Okay. This is a kink. I will answer your question. Okay. I'll answer your question. But still, there is a force. There is a net force above, right? There is still some curvature. Right? The curvature is not very high, but there is still a curvature, right?
Yes, sir.
Okay. So only when there is a curvature, there is a force. Am I right? Am I right or wrong?
Yes, sir. Yes, sir.
Okay.
So,
So
but
there is
so,
no curvature.
but in case A and B, the force is perpendicular to that curvature. But in the next case that you have just mentioned, the force is not exactly perpendicular because.
Okay. Okay. So what I'm saying, what we are measuring is the force along the rod, and that's all we are measuring because the particle is confined to the rod. It's a bead on the rod. Okay, so this here, the force, even though the force is not exactly along the rod, the forces on the sides are not going to do anything to the bead, right? Does it do anything to the bead? The bead is not going to be able to move anywhere else because of the rod, right? Yes or no?
Yes, sir.
Okay, so you don't have to worry about the forces that are not perpendicular to the that are not parallel to the rod. You don't have to worry about the forces that are perpendicular to the rod because no movement is possible along them. Okay.
Yes, sir.
Okay, but I understand your point. We will come to that in the continuum limit. These forces will vanish. Okay, these kind of forces will vanish in the continuum limit. It is because we are looking at the discrete picture. You have this kind of a thing, but when we go to the continuum limit, it will not be there. Okay, I assure you. Okay, it will be only along the vertical direction. There will be no parallel. There will be no horizontal direction force on the particle in a continuum limit. Okay, does it make sense? Yes or no?
Yes, sir.
Okay. Okay, so your force would be proportional to the curvature, right? If the curvature is more, there will be more force. If the curvature is less, there will be less force. Does it make sense? Okay. Let's say you have particles here. Let's say you have particles here. Which one will have more force?
So
The first one.
The first one,
First
obviously.
one, sir.
Yeah, the first one will have more force because it's highly curved. Okay, this is not too curved. Okay, so force is proportional to curvature, right? Do you understand this sentence?
Yes, sir.
Okay, so this is your wave equation. That's your d square y by dt square, which is force, right? Is proportional to d square y by dx square, which is curvature. Yes or no?
Yes.
Yes, sir.
Does it make sense? And the proportionality constant is just 1 over c square. That is a proportionality constant. Okay, force equals curvature. That's your wave equation. Our force is proportional to curvature. Okay.
Got it, sir.
Okay. So this is the physical intuitive understanding of what a force, what a wave equation is. Okay. When there is no curvature, there is no force. Okay. And depending upon how curved your particles are, so in the continuum limit, let me go to the continuum limit. Continuum limit means the wavelength is much larger than the separation between the particles. Okay, that is the continuum limit. The particles are really closely distributed and the wavelength is much larger. And this is where you see most of the times, this is where you see waves. Okay, the particles, the distance between water molecules is much smaller than the distance than the wavelength, right? If you take a rope, a rope, the distance between the particles that are oscillating up and down in the rope, that distance is extremely small compared to the wavelength that the rope supports. Okay, so when the distance between the particles are really, really small, you can use the continuum limit. Okay, where if you look at two particles like this, it's slightly curved. It's curved so small that the forces in the horizontal direction is very, very, very small. Okay. Okay. So the particles would not even move in the horizontal direction because you have neighboring particles that are blocking its motion along the horizontal direction. The only way that it can move is in the vertical direction. In the horizontal direction, the forces due to the neighboring particles is extremely high. So there is going to be no movement along the horizontal direction. So that's why I said it's bound to the rod. Okay, it is that is a picture that is analogous to saying that the neighboring particles are pushing it to oscillate in this perpendicular plane. Okay. Okay, so in the continuum rate, the wave equation becomes exact. Okay, no horizontal forces. Does that make sense? Yeah. Okay. Okay. So you have an idea of wave equation. This is just square root by dou t square. This is curvature. This is force. Okay, and it is just very simple. Like it is quite simple. Oops. Hold on a second. Okay. It is to understand it is quite simple. Okay, because there is a curvature, the particles, the neighboring particles are pulling it down, and that applies the force on the central particle. That's it. That's it. If there is no force on the central particle is not going to move. Okay, it's going to stay put. Okay. So a particle in at phi equals 2, phi equals pi by 2 phase point, that particle isn't going to move. It doesn't have any force on it. It's just for a simple harmonic oscillation in the center, at the equilibrium position, there is going to be no force, obviously, right? It's the same thing. At the center, there is no force. At the edges, there is a lot of force. Okay, right at the top and right at the bottom, at the crest and the trough, there's going to be a lot of force because the particles are pulling it back towards the equilibrium position. There is a lot of force there. Okay, which is exactly the same scenario as simple harmonic oscillation scenario, where the force at the center is 0, force at the edges are high. Okay, so the particles here oscillate in a simple harmonic oscillation motion. Okay, fair enough?
Yes, sir.
Okay. Okay, I think I'll stop here. Okay, and we will continue next week.
So I might have one question, but that may sound absurd.
No question is absurd. There are only stupid answers. There are no stupid questions.